Hey everybody, welcome back to the show. Today I'm on episode 124, and this is kind of an extra episode for the month. I try to publish this show every other week, try to aim for Wednesday, and that usually means about 2 episodes a month. But this particular month, we ended up that kind of extra Wednesday, and I decided to throw in this extra episode, which works out well because I haven't been really sure where to stick this. I had an engineer join me on the show to really talk about the structural side of things. And this comes out of that wood strength episode I did before. So I started editing some of this down and I realized every little bit I wanted to cut out had a cool little geeky tidbit in it. So I'm going to apologize ahead of time. This is a long episode, but you know what? I'm not going to apologize because there's some good stuff in this episode. Enjoy. You guys might remember when I was talking about wood strength, I threw out the challenge that if there are engineers out there who want to step forward and actually speak from a perspective, an informed perspective, unlike this woodworker / music major, well, I got a degree in physics, but like, if anything, the Big Bang Theory taught me is physics and engineering are very, very different. The Big Bang Theory, the show, not the actual Big Bang. Anyway, let's move on. I have Brandon Long. Brandon is a structural engineer, an aerospace structural engineer who works at a certain space agency that goes by four-letter acronyms. But, you guys know who that is. We're talking about NASA, folks. But it's important to be clear that Brandon's opinions do not reflect NASA. Was that legal enough, Brandon? Did I cover that?
I think that works.
Good. Thanks for coming on the show. I really appreciate you putting your neck on the line here.
Yeah, thanks for having me. I'm excited.
And I say that on purpose because we're going to talk geeky engineering stuff. And if there's one thing I know, there are engineers who listen to this show. And my inbox is full of, I can't believe you said this, or I can't believe you said that. So now I'll just make sure to include your email address at the end of this, and you can get all those from here on out. It'll be fun. So, Brandon, if you would, give us a little bit of your background. Let's lay out your credentials, certainly from an engineering perspective, but I'd also like to hear from a woodworking perspective.
Okay, yeah, so we'll start with the engineering side of stuff first. I am about to be 32. Grew up in Indiana, Northeast Indiana specifically, and I got my bachelor's degree in mechanical engineering with a minor in aeronautical engineering from Trine University. It's a small private school in Angola, Indiana. But so I graduated in 2015, and I saw an offer for, not an offer, but a notification of job openings at a small prototype helicopter company down here in Newport News, Virginia. And so, I've always been kind of a hands-on guy. I like the smaller organizations. And so I was like, what the heck? Let's go do some R&D and prototyping. So I went down there straight out of college, school, they teach you a lot of equations in theory, but to be honest, that just gets you started. That kind of puts some tools on your tool belt, but now you have to learn how to use those tools. And so, I spent 8 years there and built test rigs, learned how to design rotor blades and rotor systems for helicopters using composites and metallics. Very hands-on. One day I could be covered in grease up to my elbows building a test rig, and then the other day I could be crunching numbers in code and running FEA, and I had a blast. It was a blast.
It actually sounds kind of perfect, especially as that first job right out of college.
Oh yeah. I learned, it was like drinking from a fire hose, swimming in the deep end of the pool. It was actually very, very good position. I learned a lot very, very quickly, but ultimately the deadlines were tight. The stress was high. I got burned out, and I was ready to kind of move on to greener pastures. And so, I next moved to, I'm actually a contractor to NASA. I'm not employed directly by NASA. But I work on NASA Center, rubbing shoulders with the NASA civil servants. But so I went to uh, my current contractor. I've been with them for a little over a year now,
Nice.
so about a year and a half. But now I'm working in more of that researchy field, trying new manufacturing methodologies. There's a whole alloys section in our branch. So new aluminum alloys, how to apply them. We've got composite robots, laying up carbon fiber, stuff like that. So um, I'm not quite so hands-on now. More on the theory research side of stuff, but which actually leads me to the woodworking side. So,
Right. Like
you
many
know,
of us,
yeah,
you don't be hands-on. You got to find it somewhere, right?
exactly. That itch got too much, and I was, I would sit at my computer all day and never touch a tool, and I'd be like, I've got to start building something. So I've got a garage, and I started. I built one little project. I said, wow, that felt really good. I had a lot of fun doing that. Okay, let's try something else. And I'm sure many of the listeners know what I'm talking about. It kind of sucks
Yeah.
you in, and you're like, oh, I have to get more of this. And so the tool buying went through the roof, and I was out in the garage till 10, 11 p.m. and the girlfriend's like, all right, you need to come in now. It's getting late. And I'm like, oh my God, I didn't even realize it's 4 or 5 hours has gone by. It felt like 10 minutes. So,
Right.
um,
Love that flow state.
yeah, yeah. Oh my gosh. Yes. So, that's a little bit of my background. I'd still call myself a hobbyist, but I am trying to start up my own little business, Etsy store, that kind of thing.
Sure.
I, I,
You gotta feed the tool buying, right?
Yeah, yeah, exactly. I'm actually building my own CNC machine. Um,
Nice.
so I'm, putting that. I've got a little bit of electronics experience as well, so
Well, that
that's
actually
in
brings me
progress. Yeah.
kind of to my first question. So, you mentioned you're not nearly as hands-on anymore. Do you find that that is related to the job, or more to the fact that more manufacturing is being done through CNC and 3D printing and rapid prototyping and things like that? Maybe because this is all so new. I mean, I realize in some of the hallowed halls of defense and DARPA, they've been doing the 3D printing and stuff for a long, long time, and you might expect some of the same things from large agencies, like NASA. But is that why you're not hands on, or is it merely a theory type position?
It's more job theory related.
Okay.
Yeah, like there are certainly hands-on tasks and jobs in aerospace and defense, and actually, that's one thing I've noticed is automation is not necessarily better.
Hmm.
A lot of times, trying to get the robot what you want to do, troubleshooting code and that kind of stuff, it might just be easier to, pay a guy to use his hands to put down some carbon fiber. And there's no hard and fast rule one way or another. But
The hand tool guy is smiling really big right now.
yeah,
This is
yeah,
like the entire mantra of my hand tool school.
yeah,
It's like, okay, you go fiddle with the code on your CNC. I'm just gonna go saw to the line. Like,
yeah, yeah. And
everything has its place, right? But yeah, it's kind of neat to not forget that side of things and use all those tools at your disposal. That's cool.
absolutely, yeah.
Nice. So there's a couple of things for the listeners. Brandon reached out and immediately grabbed my attention because you've got a lot of experience working with a variety of materials, metallics, composites. The carbon fiber thing really raised an eyebrow because carbon fiber to me is very, very cool. I've looked into a lot as a cyclist. Certainly, I have 3 carbon fiber bikes. Played around with the material. I know several wood manufacturers who are using carbon fiber. In fact, on a recent episode, I brought up a company that is using it as part of a plywood type structure. It's my understanding, at least from a basic level, there's a lot of similarities between wood and carbon fiber. And you had actually said this in one of the emails that you'd sent to me. And that kind of immediately grabbed my attention because I think, well, listeners of the show know I'm really kind of excited about the future of the wood industry because it's coming back in vogue in such a big way in manufacturing as a renewable resource. But if we can start to combine it in true, engineered materials using composites and wood, it could be really fascinating. So, yeah, can you explain? I'm going to put you on the spot. Can you explain how carbon fiber and wood are similar?
Okay. All right. So, carbon fiber and as well as wood is a composite. And so, generally, a composite just means it consists of two or more materials. Another
Good point.
example is concrete and rebar.
Mm-hmm.
And so, each individual material has its own strengths and weaknesses. And by combining those two different materials, they can kind of complement each other. So with concrete is very strong in compression, but it's terrible in tension.
Mm-hmm.
And so that by adding that rebar in, you add that tensile strength, and so now they complement each other, and you get overall a strong material. Carbon fiber is the same way. The carbon fiber strands themselves. So essentially, assuming you don't know a lot about carbon fiber, how it's made is that, for lack of better words, they essentially just take really long plastic strands, threads, and I mean the diameter on these is tiny. I mean, probably just a few thousandths each strand, and they heat up this plastic thread, and the carbon within that plastic starts linking together, and those carbon chains create the very, very strong bonds, and so you get incredible tensile strength with these threads.
Okay.
But they're just loose, right? I mean, it's string essentially, so you need to allow that flexible fabric to take a shape, take a form. Um, and so that's where the resin side of it, of the carbon fiber, comes in. That resin, it's moldable. It can be liquid. It can be a type of like gel or goo, for lack of a better word. We can get into resin later, but um, the strength of that resin in tension is very low compared to the carbon fiber itself, and actually, it the resin strength itself doesn't really add a lot to the composite. It's the fiber, it's that carbon that's taking all the load, and so if you sever those fibers, you can't carry load. You lose load continuity, and so um, but now we can form complex shapes on a mold, stuff like that. But also now, um, with those strands, you can actually tailor the structure to be a specific direction. You can get more axial strength or more torsional strength. And now, because in aerospace, everything is about weight, right?
Mm-hmm. Right.
And so the key is strength to weight ratio. So the more precisely you can tailor that structure, the more effectively you can put your weight to work for you in exactly how you need it.
Right. And by, the process of laying up sheets or individual strands or whatever you formed in carbon fiber, you can put the strength where you need it, in other words.
Exactly. And another example, very similar, is like plywood.
Yeah.
Um, and with carbon fiber, we'll put a 0-degree layer and then a 90-degree layer, a zero, and then maybe a 45. And I'm talking, angles, 0 degrees, 90
Right. Right.
degrees. And so plywood's very, very similar. They'll lay one sheet this way, lay the other sheet the other way, and you build that. One thing that's good about um, plywood is its properties, it expands and contracts quite uniformly across its width in all the directions, and you make this kind of nearly homogeneous property structural board you can use. It's stable and stuff like that versus just
Right.
a normal board where all the fibers are going in the same direction.
Sure. So then, if we take that comparison, the carbon in wood would be like the cellulose strands, and the resin would be the lignin, right?
Exactly. Yeah,
Okay,
exactly.
right. So it's actually interesting, the technical definition of composite. I'm glad you said that because in the wood world, we always refer to composites as, particle board and OSB and plywood, and really like composite decking where you've got a wood flower core and an ethylene outer shell or something like that. And it's actually an interesting way of looking at it. Wood, natural wood, is a composite material because you've got cellulose and hemicellulose and lignin, along with a bunch of other stuff thrown into this. I don't know, would you call it a matrix?
Exactly.
I
Yeah.
guess, yeah. So carbon fiber is very much the same way. You can lay it up, put it in a form, which you're kind of building this matrix that has engineered, like your force vectors are aligned. We know the strongest direction, of this particular carbon fiber, and if we lay it this way, it resists the force. If we lay this one this way, it resists the force this way. And I'm looking at the bottom bracket of my bicycle right now and imagining how the fibers were laid up around that turn because there's so much force in a lot of different directions, right down at the bottom of that bicycle. It's really kind of cool. And in many ways, when we build furniture or you build a house, our joinery is kind of doing the same thing. Like, we don't want to necessarily, like, we know that a board is weak across its width, like across the fibers. You can split it along those fibers. The lignin, like you said, the resin isn't really that strong. It's just kind of holding it together. Well, I shouldn't say that because lignin actually is quite stiff. But if we wanted to like make a 90-degree turn, say you've got a table leg into a table apron, you couldn't just take like a big wide board and cut like a right angle into it. That apron or that leg would be super, super weak because you'd have cross grain. So by taking a long grain board, joining it at 90 degrees to another long grain board in the leg, you now have strength. We can just do that with carbon by laying it up and putting it in a mold, in other words. It's pretty cool.
Exactly. Yeah.
Interesting. Forgive me, listeners. I'm going to go off on a bit of a tangent here. Um, I don't know how much this has to do with wood, but can you explain like the different qualities of carbon fiber? Like you've got, 800 series and 700 series. Everybody has these different numbers. And, to me, I've always been like, this is just higher quality carbon fiber, or better refined or better manufactured carbon fiber. Do you know what I'm talking about here?
Kind of. So um, a lot of the composite I use is it's very common in aerospace is IM7/8552. So
Mm-hmm.
IM7 is describing the fiber itself, and the
Okay.
8552 is for lack of a better word, it's a part number of resin from a manufacturer called Hexcel. And so that IM7 actually stands for intermediate modulus. I think it's 7 million.
Okay.
Don't quote me on that. We just typically use the acronym, but um, so they have different moduli of fibers. So there's actually an IM10, which
Mm-hmm.
so obviously the modulus is higher on that one, and so modulus is essentially the stiffness of the fiber. So
Right.
yes, and then one of the most important things are the um, the types of weaves. So you can weave these fibers together, or you can have them all running in the same direction. So you can get like the robot we've got at my NASA center. He uses unidirectional tape. So that unidirectional means all of the fibers are running in a single direction. It's essentially just a big spool of thread and it's got resin already impregnated into it.
Hmm.
And so it'll lay down these unidirectional tapes on the table. But if you buy like a plain weave fabric, there's specs on how many threads per toe that they weave together. Um, just
Oh,
like with
okay.
like
Like your
your
bed sheets.
bed sheets, you've got
Yeah.
700 thread, 200 thread, all that
Right.
stuff, and
Okay. Okay.
it's essentially the same kind of idea.
Interesting.
Yeah.
Interesting. So I knew at heart there was some, difference in the modulus, especially like, and again, I'm staring at carbon bikes right now. Um, we in the bike, I don't work in the bike industry. What I'm saying, we cyclists don't really have exposure to aerospace grade carbon. There's been carbon fiber, I should say. There's been several manufacturers lately who've said, hey, we're now using aerospace grade carbon fiber. And that's always been like, the Shangri-La, it's the finest carbon fiber. I've understood kind of in passing that there were different strengths in a very generic firm, or stiffness, that the modulus number was going to be different. But I had not thought actually about the thread count, if you will. That's very fascinating.
Yeah.
It was always to me like, it's kind of like when you think in terms of finishing or mineral spirits. Naphtha is just a more refined version of mineral spirits. That was always my understanding, and that's actually sounds like that's incorrect. That's interesting. Very cool.
Yeah, it's funny. It's funny you mentioned like the aerospace grade, and I always kind of is one of my pet peeves, and not to get off on too big a tangent here, but um, I hate that buzzword aerospace grade because it doesn't mean anything. You know, we use all kinds of aluminums and composites, and like it's not like, oh, we'll only buy aerospace grade stuff. Now fasteners are a different story. We're not going to go buy structural fasteners off of McMaster-Carr that comes from some unknown factory in China. We have very strict specs for that, but like we'll use all manner of materials, and so I just had to get that off my
Right.
chest. It's always funny when I hear that phrase aerospace grade.
Yeah, no, I get that. I think most industries can say that. Although I'm sure that you're paying aerospace prices for
Oh,
your materials.
for sure.
There's the difference right there, right?
Carbon fiber is not cheap, that's for sure.
Right. The carbon fiber that the like Trek Bicycle Company is buying is not quote aerospace grade, meaning it's cheaper
Yeah,
than what
yeah,
than what NASA and Sikorsky and McDonnell Douglas are buying. So yeah,
right.
it's ultimately what it comes down to. Yeah, we
Yeah,
we hear the same thing in the lumber sector. Oh well, this is commercial grade. What does that mean? That means nothing. It's still wood. What's the grade on the wood? Yeah, it's everybody's got their own little things there. But I think it's particularly interesting, though, when we start talking about material science in general. And this brings us back to lumber. Thank you, folks, for being patient here. Ultimately, it's all material science, right? It's wood, it's carbon fiber, it's aluminum, it's ceramic, and understanding loads, understanding like force vectors, and understanding the properties. I've harped on this so many times on this show about technical properties. I think it would be really interesting from an engineering, a structural engineer perspective, to kind of talk about loading in a generic term. So you've already thrown out several terms. You've mentioned tension, compression. We can talk, I think, about torque or bending strengths, things like that. All different forces, stresses, maybe would be a better way of putting it. And ultimately, these technical numbers that I often talk about, the modulus of elasticity, it's stressing a particular load scenario, I guess, until it fails. Correct?
right. So modulus of elasticity is essentially a spring rate. If you imagine you hang a spring vertically hanging, and you put 10 pounds on it, does that spring deflect a tenth of an inch? Does it deflect a half inch, 1 inch? Um, Spring rates are usually pounds per inch. How many pounds does it take to elongate the spring 1 inch?
Mm-hmm.
Modulus is the same idea. How many pounds and the units are psi, but essentially, how much force does it take to stretch the material a certain amount? So it's a modulus of elasticity is inherently a tensile type um, effect.
Right.
There's also shear modulus of elasticity.
Yeah. And shearing strength shows up. It's a little bit more difficult technical property to find in wood, but I've always related that to like how easy it is to hand plane, frankly. I mean, certainly how easy it is to plane in general because you're removing wood parallel to, those cellulose fibers. That's the direction of force in shear. So certainly it applies to a planer, a powered planer or a hand powered planer. It's just, you don't really feel it there. The machine's doing the work there. So the hand plane, you can actually feel the difference in shearing strength. If I take a piece of, grenadillo and attack it with my hand plane, and then I go over and take a piece of butternut, same plane settings and one pass is not going to dramatically alter the sharpness of that blade too much. But if you really want, you can sharpen it again. You will notice a dramatic difference in the force required to push that plane to pull up the same thickness of shaving. That's the shearing strength. Now, there's a dramatic difference. I don't know the numbers off the top of my head, but I can tell you there is a dramatic difference between butternut and grenadillo, or God forbid, ipe or something like that. So let's talk about, well, from a wood perspective, what and give me some vocabulary here. What load scenarios, I guess, do we need to be concerned with?
The biggest one is going to be bending.
Okay.
Um, I've heard you say on a previous podcast, kind of vertically crushing a member is incredibly difficult.
Right.
Um,
Yeah, it's the
tr- tr-
strongest bit of wood.
right, right. And so, trees, they grow vertically. They have to, that trunk has to vertically support that entire rest of the tree above it. And so
Mm-hmm.
they're naturally evolved to be very strong in compression like that. And so, when you think about when wind hits the top of the tree, you're bending that trunk, and which induces some stress on it. And
Mm-hmm.
that's why those one of the reasons why those fibers are all unidirectional or mostly unidirectional running up that trunk. But the
Well,
biggest thing is bending.
can you classify bending as its own entity, or isn't that really just tension and compression?
Correct. Yeah.
Tension on one
So
side, on the convex side of the band, and compression on the concave side of the band, correct?
correct. Yeah.
Okay.
Yeah.
So, and because we have the term bending strength, which, yeah, that's useful. But I think breaking it down into tension and compression might actually, for the woodworker, I don't know. I might be digging into that a little bit too much. Um, so if bending is kind of the most important thing we look at as an engineer, when you look at technical properties, what's interesting you?
So I'm looking at and there's actually so with wood, well, with metals and composites, we have ultimate tensile strength. That is the stress on which the fiber will fail. It will break into separate pieces. That
Uh huh.
is, that is ultimate failure. Um, I believe in, I'm not so familiar with the wood side of stuff, but the modulus of rupture is the same idea. When,
Mm-hmm.
that is in more or less an ultimate tensile strength, but it's induced using bending. That bottom
Right.
side when you load up that beam is in tension, and assuming it's a straight grain, nicely clean board, you'll fail that fiber in tension on the bottom.
Right.
um, and so that's I'm looking at, um, and maybe we can get into this, but my uh, uh, mod, uh, my inertia, my cross-sectional moment of inertia of my
Mm-hmm.
beam. I'm looking at the span, right? You can imagine if you put 10 pounds on a 3-inch long board, what that might feel like versus a 10-foot long board. It's going to
Right.
be an extremely different experience, even though the load is exactly the same. And so, yeah,
And for that matter, the thickness of that board will change that experience as well.
absolutely, yeah,
Which is, it's one of the reasons that it's a long, like commercial boardwalk construction versus residential deck construction have different codes as far as span. Now, in many instances, the span ends up being the same, 16-inch on center, but the thickness of the deck member needs to change. So you can put a 3/4 or even a 7/8. They'll sell some 5/4 inch thick decking for residential, but for the most part, your decking board's going to be around that 3/4 inch range, and you're totally fine. You're not going to get a springiness in your step because it's just your family, and your friends walking on this. On a boardwalk, however, you've got thousands of people, bicycles, trucks, all kinds of stuff rolling along the surface. So the requirement for commercial boardwalks is using a 2x or 1.5 actual with the same span. So you increase that thickness in order to prevent that springiness, that bending, that deflection that you would see. Yeah.
exactly, yeah. And so, with bending, your stiffness and strength go up with the square of thickness,
Mm-hmm.
whereas it only goes up linearly with your width. So, in aerospace is one of the things I'm constantly thinking about every time I design a part is everything is weight, right? So, if I can it's just, if I add the same amount of material as width, I won't get as much bang for my pound, bang for my buck, as I will in height. So I'm always trying to make items as tall as possible, as thick as possible, and utilize that weight. And so that thickness you're talking about on that boards is exactly what they're doing there.
Mm-hmm.
And the other thing is, what's your worst case loading scenario? Um, Generally, it's something you might not think about. With a table, one plate on the table, whatever, nobody's going to think about that. But what happens when your drunk college friend comes over and invites 4 other people to jump up on your table and start dancing? That's an entirely different loading scenario.
Yeah, good point. And to go back to my earlier example, all those boardwalks are designed really well until Mother Nature came along and threw a hurricane at them, and suddenly, no more boardwalk. So they were
Right.
they were engineered to a point, and then I guess as an engineer or as a builder or anything, you have to say, okay, well, there is always a worse case scenario than what I've planned for, but at that point, we've got bigger problems to deal with. So, you can't necessarily plan for everything, I suppose, but you could, but then you're going to pay for it, in some way, whether that be actual cost or weight, performance, something along that line. Hobbyist woodworkers, we often joke that we over-engineer everything because we can, because we're not necessarily trying to meet a price point, or we've got all the time in the world sometimes to do this stuff. There's no exterior demands on us to prevent us from doing things. So, I'm going to dovetail that into a tenon with a screw. It's like nothing. So now my 4 drunk friends can dance on my tabletop.
Yeah.
Whereas that table that I bought from, some commercial manufacturer, even a really good commercial manufacturer like Thomas Mosier, fantastic, beautiful commercial furniture. But yeah, your 4 college roommates dancing on the table might be a problem. Whereas the one that like Joe Woodworker built in his garage might actually be better, be in better shape.
Yeah. And this is one of the things is with design is like, what are your objectives?
Mm-hmm.
Because woodworking, and this is one of the reasons I love woodworking, is if you take a Venn diagram, it's a mix of all these different professions. You've got art, right? Yeah, I mean, woodworking is art.
Mm-hmm.
You've got structures. So you've got some, you know, physics there, some material science type thing, but you've also got a little bit of chemistry with your finishing,
Yeah.
oil based, water based, alcohol for shellac. Um, and so you take all of these different skills and knowledge and profession, and you kind of bleed that Venn diagram together to produce an object that is both beautiful, pleasing to the eye. But it also accomplishes the functional task it's set out to do. Um, you can imagine different scenarios where if all we were cared about was structure and we didn't care how beautiful it was, the solution would be very, very different than if we just only cared about art and didn't really care about the function.
Right.
And, you know, and then there's a whole nother business side of it as well. If we have to hit a price point, a certain profit margin, that kind of thing, that brings in a whole nother dynamic. And so it's always a delicate balance between all these factors and weighting them and deciding what's the most important thing here.
It's actually a really good point. One of the guys that I really learned woodworking from is Chuck Bender. I was very fortunate to take a lot of classes with him because his shop used to be much closer to me. He's up in the touristy district of the Pocono Mountains now. It's much further away, but he used to always joke about, this is woodworking, folks. This is not hard. And he would point himself. He's like, look, I've been doing this for 30 years. It can't be hard because I'm doing it, and I'm an idiot. But you know what? The woodworkers I've met are some of the smartest people, or at least some of the most aware, kind of cross-disciplined individuals. And I think you just kind of hit the nail on the head there. It's a lot of different stuff. And certainly there are woodworkers out there who don't touch finish and ship stuff off to a finisher because they've put so much effort into this, and they don't touch the chemistry side of things. But even if you're one of those, like all the other stuff that you just mentioned, it's really kind of fascinating. There's no wonder there's so many woodworking geeks out there because you kind of have to be.
Yeah, yeah.
So let's look at this again from a wood perspective. So we need to understand load, particularly as we're talking about bending. We need to understand like safety. Building something that's not going to fall apart under load. But we still have that limiter of strength to weight. Like if weight were not an issue, we could over engineer a lot of stuff, but you gotta move that chest of drawers at some point. Even if it's just to move to vacuum behind it, that's kind of a big deal. You got to get it out of your shop and up the stairs. So weight is kind of an issue. And then you have that balance of design. Like that's that balance we're dealing with. We could over engineer everything. And I think this is like the evolution of a woodworker. Woodworkers to start out, and just about every woodworker I've talked to is always like, am I making this strong enough? And especially the new ones who don't have a lot of experience building furniture, they're very concerned they're going to build something that's going to fall apart. So they overbuild it, and they often use thicker parts in order to do that. Then you get a little bit more experience under your belt, and you start to kind of play with design. And it seems to me, especially these days, design, it's about making things lighter. It's about making things more delicate. The thinner you can make that board, whether it's by adding a bevel on it to make it appear to be thinner or actually making it thinner, how tiny can I make that dovetail joint? These are the things that give that design elegance. And I'm being, very broad here. There's whole other design schools that rely upon weight and things like that. But then even that's a balance, where the balance between weight and light can change the feel of things. But ultimately, as you said before, if all we were concerned about was building something that doesn't fail, it would all be very clunky. Like it was in a Minecraft game or something like that. Trying to get those younger viewers in. So from an engineer's perspective, if you're going to build a piece of furniture, I'm trying to pull this all together. We want to strike that balance, right? We want to push the envelope a little bit, and like thin up that board, make that curve a little bit tighter so you get more flow. But the minute you kind of increase, or I should say decrease the radius of that curve, then you're cutting across the fibers a little bit more. There's a good example. So let's go back to my table example. We've got a table apron, and we want to put like an arched bottom into that apron. Because again, from a design perspective, you add that arch in there and you're going to lighten the whole thing. It also gives you very an architectural feel. Think like Roman barrel vaults and like the Arc de Triomphe and things like that. But as you start cutting that curve into the bottom of that board, you are severing those long fibers, which is weakening that board. So what am I trying to say here? From an engineer's perspective, what's happening there? And what do we need to be like considering as we alter and play with that curve? What are the elements that at play? Certainly the length of that board, the overall length of that apron could be a concern. I guess the radius is of the curve is a concern. From your perspective, what's going on in your head as you're walking through that exercise?
Yeah, I mean, you're very right. It's balance there. So one thing is having that tactile experience as well. It's one thing to just look at a solid model on a screen and just estimate something like that, but nothing beats having an actual piece of lumber in your hands. And as you cut it, you can and you cut that arch into it, you can probably feel it's getting a little bit springier, a little bit softer,
Mm-hmm.
and eventually you will get to a point where like you would severely weaken that board. But again, going back to loading, you know, you probably won't even find the limits of that strength unless you're under an extreme loading scenario.
Mm-hmm.
And so, while you were saying like you're cutting all these fibers and stuff, this made me think of like bent laminations. Um, let's say you wanted load continuity all around a curved member. Let's say you have a big flowing, like an Eames chair or something like that,
Okay.
and you want that load to carry through that member and whatnot. That bend lamination would be a very good solution because those fibers are intact and you're essentially redirecting the load. You're curving that load. It's following those fibers. Whereas if you just cut a curve into a board, and load it up, you're gonna split that board because those fibers are no longer oriented in an appropriate direction. And now you're relying on that ligament strength. Um,
Right.
yeah. So again, going back to that height, height is everything. You get a square return on your height. So every little shaving you take out of that is, it's an exponential decrease in strength. Um, so that just my thoughts.
No, I'm actually really glad that you said that because that was the thought that was running through my head. Um, so let's quantify height and width because they're very relative terms. In relation to the board, in relation to the structure of the wood, height and width, like if we're on like a, Cartesian grid or whatever, the x-axis is the height, no, the y-axis, sorry, uh, is the height. But like, as the apron runs across this table, the height is that vertical dimension. You know, the width, I guess we would see. You see what I'm saying? Like it very
Yeah,
quickly terms like height and width and thickness. It all depends on how you're looking at it.
it's
And
it's all the loading. It's how is your load oriented to your cross section.
okay, good point. Now, because wood is oh, I'm forgetting the word. What are we talking about? It's not isotropic. Well,
Orthotropic.
orthotropic. Thank you. I was going to say anisotropic, which I guess is kind of the same thing. So because it has different strengths in different directions. It's orthotropic. This is where, and you said it earlier, like the physical working with the board and you feel that flex. I have gotten in trouble so many times in SketchUp, or pick your favorite CAD or modeling program, where I'm designing something and then I actually get into the shop and I realize, oh, I just had a cross grain situation. One of these days, I'm going to be able to record a podcast without Kenny barking his fool head off. But I guess he's just as much a host of this show as anything else. But anyway, so I apologize for the barking dog. So oftentimes, I'll find myself in a situation where I've inadvertently, had this real short grain situation because of how I've cut it. But you can solve that problem by altering the dimension elsewhere. So you talked about what was it? Linear progression across the width, but an exponential progression across the thickness. So let's take this table apron and say you want to make that curve, like the apex of that curve is really thin. Like this looks really cool if the curve, say we've got a 4-inch wide apron and the curve comes to a point at the top where now the apron is only a 1/2 inch across. So you've got this really tiny little sliver. That, certainly that board, if that were a 3/4 inch thick board, it would fold right in the middle there. But if I increased the thickness of that board from 3/4 to like 2.5, are we getting more strength there?
You are getting more strength, but only in a linear fashion. So,
Okay.
this isn't a math show, but for a rectangular cross section, which most boards are, it's base times height cubed over 12, and that plays into the bending equation. But so if you double your base, you only double your strength. If you double your height, you 8 times your strength, you 4 times your bending strength. Yeah. So it's more. There's nothing you can add strength that way, but you're going to have to use more material, and maybe now it starts to become a little bit visually clunky. And
right.
You've achieved your strength, but now it's like the proportions are off.
Yeah, well, but that also depends upon perspective too. Like in a table apron, you're probably never going to see it. For that matter, like this example of having a deep curve, so you've only got that 1/2 inch connective tissue. Well, what's the overhang of your tabletop? Like you're never going to see that. The dogs on the ground might see it. Maybe your child crawling around might see it. But those are interesting points. So I guess let's talk a little bit about like wood being an orthotropic material, and actually carbon fiber as well as an orthotropic material. I mean, you said bent lamination before. That's essentially carbon fiber. You've taken these little thin strands of wood and you've put them into a matrix with, a resin, whether it's Unibond or polyurethane glue or PVA. All of these equations that we've thrown around, and we certainly don't want to get too technical on that side, mainly because this is audio. Does this, the equations that you're citing here, or shall we say the rules that you're citing, this applies to orthotropic materials?
Yes, for the most part, yes. If you look at those orthotropic material properties in an average general sense, when you're talking about a structure at large, you can kind of average out the resin and the fiber and treat it as kind of one strength and property. When you start to get down to the individual, loading, whether you're actually trying to split fibers from the resin, maybe I'm getting too fine here, but
not unless you're a chair maker.
Yeah, well, but no, the equations and everything certainly do apply to orthotropic materials. I mean, it's physics, right? And physics applies to the materials, so they're certainly applicable, for sure.
So where I'm going with this is we have wood strength properties, or more importantly, tests that we perform on wood to give us a number, a specification. And we've talked about, the MOE, the MRR, the max compression test, the Janka hardness test, all of these things. So from an engineering perspective, let's talk about what these mean. I've had a show of like what the tests are and kind of what they mean. But because all of this, everything we've talked about to this point is kind of leading up to this point. We're going to try to put a bow on this. Now we've talked about, loading scenarios and failure and how things could be different in an orthotropic material, depending on, where the force is, where the load is across that fiber. We haven't even really begun to talk about the internal structure, which I talk about a lot, which ultimately is what changes the number. Like if it's a ring porous wood or diffuse porous wood, these are the elements that give you different results. So what do these numbers actually mean with these strength properties, and how do we actually use these numbers?
Well, so actually, so like MOR, modulus of rupture, would be very useful for a bending scenario. I mean, that is ultimately what that test is. It's a bending test. So that if you've got something a member spanning a distance and you're going to put load on it, that's what you want to use. A crushing strength, which in all honesty, I'd be surprised if you really need to rely on that in a furniture type situation.
Or in any
But
situation, really. Any
yes,
situation using wood, it
well,
just seems.
yeah, something like that may be more applicable if you're, like, let's say you are building a giant ship in a dry dock and you want to rest the hull on wooden planks to protect the steel because you don't want steel on steel. You could theoretically crush that wood under that ship at that point, dunnage for lifting and stuff like that.
Yeah,
So,
we actually
yeah,
sold a fair amount of material for crane mats and for shipyards for that particular purpose. Steel mills at the same time for rolling underneath the rolling out of steel. We used in many instances. Sometimes maple was used because of its high crushing strength. So yeah, but I mean the point is we're really talking like heavy industrial type large scale construction where we have to really worry about crushing strength when it comes to wood.
right,
And
right.
if it got to a point where wood would fail, it would be in an application where we probably wouldn't be using wood as the material of choice anyway. So
Right.
yeah,
Yeah.
I rightfully look past that number a lot of times.
Yeah. An important one might be Janka hardness.
Mm-hmm.
Um, uh, that in similar in the aerospace and stuff for metallics and stuff, we use Brunel strength.
Mm-hmm.
And it's the same idea. You take a steel sphere and you press it into the wood. Um, this is good if you want to do like a desktop. If somebody's got a ballpoint pen and they're writing on a piece of paper on their desk, you can, and I think you had mentioned this in one of your other shows, but you could very much, the pressure could be high enough that you can put your writing into the surface of your desk. So,
Yeah,
like
tell that to the guy
like,
who filled out a job application at my desk one day when I wasn't in the office, and
yeah,
now his job application is faintly imprinted into my walnut desktop. I'd
exactly.
like to
So,
find that person someday. Talk to him about that. But here we go. We're back to orthotropic materials here because the Janka test is specifically pressing a steel ball into the face of the wood. So perpendicular to the long grains. Whereas crushing strength is pushing it into the end of the wood, parallel to the long grains. So this is the other thing about these tests is it tells us, Janko hardness. What does it tell you? It tells you how hard the wood is. Well, how hard the wood is in what scenario? How hard the wood is, like when you're pressing down on the face, like you said, in the case of a desktop. But if you did that same test with a, zero point 0.5 millimeter or inch, zero point 0.5, I can't remember, it's a half-inch ball, and press that into the end or the top of that table leg, you're going to get a very, very different number. And that's not a Janka test anymore. So that's the thing that I'm constantly kind of telling people is these numbers are very specific tests and very specific orientations on the material itself.
Right. Yeah. In all honesty, if I were to try to teach somebody, how to use these values to design a piece of furniture, the biggest thing is that modulus of rupture. That's going to be your just general, I've got a shelf spanning a distance, or I've got a tabletop, that's going to have load in the middle of it, or an angled chair leg, that kind of thing. If you're going to fail wood, in the context of furniture, it's almost always going to be in some type of bending scenario.
So what about modulus of elasticity then? Why is that not as important?
So,
or is it?
It is important. So, strength and stiffness are actually somewhat independent. You can have a very soft material that's very strong, and you can have a very stiff material that's very weak. And right, and so modulus of rupture would be the actual failure point when it breaks in half. Modulus of elasticity is more of how deflection, how springy is it? If you put a bunch of shelves or a bunch of books on a shelf, how much sag are you going to get in that shelf? You may not break the shelf, but now it looks terrible because it's sagging, and people are going to be like, wow, your shelf looks terrible. It's still holding the books, but if we consider aesthetic part of our design requirement, we've now violated one of our requirements by allowing it to sag too much. So you could keep the same dimensions and change the material, or you can keep the same material and change the dimensions. They work together.
Now let's talk about fatigue. And one of the things that, the wood people are all excited about these days, especially when you get into, LVLs, CLTs, is that wood has a better fatigue rate, better fatigue resistance than a lot of metals. At least that's my understanding. Plastic's the same way. So, but going back to this idea of you've got a shelf and it's sagging in the middle. Yes, it looks terrible, but isn't there also a higher rate of fatigue at that point? While that shelf is sagging, it's only going to continue to sag more and more and more over time, and potentially exponentially, I think. Can you talk about fatigue at all?
I can. I can talk about it in the context of aerospace. I don't know a lot about fatigue on the wood side of stuff,
right?
But
yeah,
I can.
My understanding that
yeah.
wood is pretty good when it comes to this type of thing. It springs back and it holds its shape, a lot longer, and it doesn't metal. Well, plastic is a good one. I always use the credit card example. They tell you to destroy your credit card. So if you start bending it, you get that kind of white line that appears on the credit card as that material is stretched, and it's fatiguing, and eventually it will just snap. If you bend it back and forth enough, you can do the same thing with steel. Certainly, a little bit more force required. So yeah, I'm curious how fatigue plays into all this.
Yeah. So let's get your example. There's actually incorrect.
Okay.
So there is a difference between fatigue and repeatedly yielding a material. So when you yield a material, you permanently deform it. It will not go back to its original shape. And if you continually yield it over and over and over again, you work harden that material. Just like if you're
Okay.
forging a piece of steel or something like that, you're work hardening it. Um, until eventually you've yielded it so much and work hardened it so much it cracks.
Okay.
That is different from fatigue. At least, again, I'm speaking from aerospace experience here, but fatigue does not imply yield. Um, you can, and this was a problem in old warships. Fatigue in metallics and composites is actually a relatively new field and knowledge. It's only come around in this, I think, since the mid-century, maybe the early century, early 1900s to mid 1900s. But um, we had warships crack in half because of the flexing at sea, and so you can flex material over and over and over again, even though you don't yield it, and eventually you'll develop a crack. Aluminum is notoriously bad for this. A lot of aircraft have been lost due to aluminum fatigue. Steel is much better. Um, I think carbon fiber is pretty good with fatigue as well. Um, so that's kind of repeated loading. And then there's another thing called creep, where creep,
Hmm.
and this may be what you're talking about, but creep is if you apply load and it's a constant load, the material will continually deform over time. So,
Yes. Yeah.
and this is maybe what you're thinking with the sag and a shelf is you put books on there and it it sags a little bit, but you come back a month later and it's sagged even more, even though the, the amount of books didn't change, that material is slowly creeping.
Right.
And so, whereas fatigue would be you put the books on, you take the books off, you put them on, take them off, put them on, take them off, do it thousands of times, that material will start to develop fatigue cracks. And they
And
start,
it's
yeah,
almost invisible. In other words, there's not like if there is sag, it's springing back to its original form or whatever. It's flexing, but it's
exactly.
not deforming, if you will. That's interesting. I'm really glad you said that because I have used that credit card example a lot, and you're right. That's wrong. I like
Yeah.
it. I learned stuff. You win. You. That's all I want out of this show. Okay, so this is particularly interesting though, because when you're thinking about in furniture, fortunately, a lot of furniture loads are static. But when you start talking about chairs or drawers, moving elements, you now have dynamic loads, and fatigue could actually be an issue there, where you're constantly moving that drawer in and out and in and out and putting stuff in it, or you're constantly sliding that chair in and out from the table, leaning back on the chair, things like that. You might have some flex, and hopefully you probably have some flex to kind of what's the word I'm looking for? Kind of distribute the load a little bit. But eventually, if fatigue set in, you'd lean back on that chair, and that chair leg would just snap catastrophically. You would have failure right away. Now that may take a very long time, and that's one of the nice things about wood. So fatigue is probably not a term that we should be using with wood at all. This idea of creep is probably more important. And what else we were talking about? Yield?
Yield. Yeah.
Yeah. How interesting. Okay. So can you tie those back to some of the numbers that we look at? Like what property would indicate that this piece of wood might be more prone to yield or creep? Is that a lower elasticity number?
It's kind of independent, to be honest.
Oh, okay. Okay.
Now, fatigue and creep are stress related, and
Yeah.
so um, I
Constant
sup-
pressure, in other words.
right, and so I suppose you could tie it back to modulus of rupture. If you have a stronger material, your it will be able to better take the stress. I mean, that's just a simple fact.
Right.
But as far as I know, at least, in like the database type numbers and stuff, there's not much to describe creep or yield or things like that. you would need a separate test, and then listed how many loading cycles you were able to
Yeah.
get through, or the creep rate under a specified amount of load. So,
Well, we
but
do see
yeah,
this in consumer products testing where, you see those robots that are constantly sitting in a chair and standing up and sitting in a chair and standing up, and they're causing that chair back and that chair bottom to flex, as that weight is put down on it. There are robots that open drawers and close drawers,
mhm.
millions upon millions of times. And I guess there really isn't the real complexity of this issue is it's more of a system that we're testing. So creep and yield on a species might be hard to say because it's more of the the loading in context rather than an abstract. And there's more than just that board. Like we could probably run a repeated stress test on a board to determine maybe a yield or a creep number, but what appreciable data would we get from that?
Right.
Whereas
Yeah.
loading a chair seat over and over and over again, that gives us some useful data, but that's not the species of wood. It's how that species of wood was formed into the chair seat, how the chair seat was attached to the base, how the base was constructed. All of that system is what gives you the appreciable result.
Yeah,
Correct?
and correct. And one thing in engineering we always think of is failure modes. How
Okay.
can this fail? What could go wrong, honestly, is what we ask ourselves. What's the worst case scenario here? And so with the drawer slide, you've also, you've got friction. Are you wearing that wood away over time? And now you've introduced a bunch of slop into that drawer slide to the point where it gets bound up, or where it's not as pleasant to interact with anymore. Because remember, we can't forget about the art side of stuff. What's your
Right.
customer going to think when that drawer wears away and now they've got a sloppy, clunky drawer that's frustrating to use? And so, in that scenario, maybe you want to use a harder material that's more wear resistant from friction, or um, you had mentioned brittle. What kind of glue are you using?
Mm-hmm.
Is the glue really stiff? So let's say you use like a PVA glue. Um, as you repeatedly load that and everything, you may crack that PVA glue. Um, versus like a hide, or a hide glue, or like a silicone.
Mm-hmm.
That silicone has more flex to it, and it's less likely to fracture, and it may be more resilient. Not that I suggest using silicone as an adhesive, but like quartz countertops are attached with silicone to, got some expansion and contraction there. I think the key thing is think about failure modes. Think, how can this thing fall apart? How is it going to be used? And what will happen when it is used that way over time?
Right. I think that's our big takeaway here because let's kind of you're an aerospace engineer, so let's land this plane as we kind of wrap up this conversation. I'm gonna guess. Actually, I think you might have said this in an email, but I'm gonna guess. Even as an engineer who could do the math, you're probably not doing the math a lot in your own wood shop because let's be real, for the average woodworker, we're not building things that, minus the four drunk, college roommates, we're not building things that are going to undergo that much stress. But I would imagine as an engineer, thinking about failure mode is something that's kind of running through your head a lot. So I don't know, am I wrong? Are you doing a lot of math in the shop?
No, generally
Okay.
for my furniture, no, no.
It's good to hear because I say that a lot. I say like people don't pay attention to the numbers because the numbers are so much higher than anything you're ever going to need. Pay attention to the numbers as relative from one species to another. And I think there's the takeaway is if you're thinking in failure mode. Actually, no, I'm not going to put words in your mouth. So if you're designing a piece of furniture and you're thinking about failure modes, how does that inform the wood that you use? You personally.
Me personally, honestly, it's aesthetics first.
Okay.
What does my customer want? You know, if they want a walnut something, and I'm like, well, I want it to be stronger, so you should buy this hickory or maple. They're gonna make, yeah, but I want a dark wood. I want walnut. Like,
Right.
right. So that's the first thing. Second thing is cost. Um, you know, uh, do I have a budget to hit? Um,
Right.
and then after that, once those parameters are set, then I can start to think about, okay, how strong and robust do I want this thing? And then I start thinking about the actual physical geometry of the piece and designing it. And I use CAD. I use um, you know 3D modeling to model all my pieces.
Sure. So, do you think it's a safe thing to say that most of the, let's just use your terminology, most of the failure modes that we need to be concerned with when you think about the strength of your average species of wood, and taking into account like the typical 3/4 inch thickness, that's the ubiquitous thickness. That's the most common thing you see just because of the way lumber is milled. When we're dealing in those sizes and the average wood species, I would think the biggest failure mode that we need to be concerned with is more of a cosmetic failure, scratches, right?
Absolutely.
I
Yeah.
mean, certainly repeated scratching. I have a piece of casement molding in my house that has experienced catastrophic failure. It's actually broken in half due to a 165-pound golden retriever constantly scratching at the door to go out in the backyard. And he wore away over time. But, your typical failure is more of a cosmetic thing. You think that's a safe assumption?
Yeah, I'd say so. I mean, there does come a point where it's not strong enough, but I feel like you would notice first. Um, you would notice this furniture is very springy. It's very wobbly. It's very
Hmm.
when something is strong, you can feel it, right? When a countertop is solid and you know pound your fist on it, you can feel it's strong. Whereas if you have some flimsy piece of material, like you can also tell that. So a lot of times it just comes down to using your intuition and that feeling. And it's so go out into the shop, get a piece of wood, break it with your hands, stomp on it with your foot, and be like, "Wow, that was really difficult," or "Oh, that was really easy," and you can start to develop an intuitive understanding of how wood behaves,
Right.
I suppose.
Yeah. And I think therein is kind of the fun of all this. Like, because you can push the envelope and you can make really delicate designs or really thin, flimsy, if you will, designs that are ridiculously strong through structure. I'll go back to my Wright brothers episode when I look at the Wright flyer. Speaking of strength to weight ratio, right? And I mean, you're in aerospace. It's all about strength to weight ratio, and looking at things like bridges, timber frames for that matter, all of the skeleton that is created, and you can create sometimes very, very delicate looking things that would be flimsy if you didn't think about those failure modes, the directions of force, and how do we bolster this without like increasing the size of each individual member. That's the fun part. I think that's that Venn diagram you talked about between design and structure that could be really fascinating to play with.
Exactly. Yeah.
Cool. This has been fascinating. I hope people listening to this are not like, "Good Lord, what's going on here?" But the takeaway and really why I wanted you here, Brandon, is to kind of let's talk a little bit about the science. But I think ultimately the takeaway is don't overthink it. Like, be aware and think about failure modes. But you really got to push it with wood. before things really start to catastrophically fail. Now, over time, these things like yield and creep are kind of interesting, and I think it would be interesting to I'm going to think about that a little bit more over. This may be one of those things as well, like you talk about, where fatigue is only very recently, because frankly, we didn't start experiencing it. Like things hadn't been around long enough, before for them to fatigue. So as more and more people are building furniture over a longer period of time, you'd be curious to see how things hold up. And do we see yield over time as that possibly slightly loose mortise and tenon joint starts to see greater compression, because every time it's loading, it's shifting a little bit, and it's that moment of inertia as it slams into the outer wall of the mortise and it shifts around a little bit. That type of stuff would be causing yielding over time. That's really fascinating, and we could turn this podcast into another hour if we went down that rabbit hole. So seriously, thank you. This has been kind of cool. Do you have any kind of any takeaways for the wood users out there? Are there any kind of rules of thumb, or maybe documents, or I don't want to say equations, but any things that like people could consider as homework or to review when they're thinking about failure modes and such? Because let me qualify that. Let's talk failure modes in general. I built a fair bit of furniture. You've built a fair bit of furniture. Some of this stuff is kind of obvious to us. If you're new into building furniture, just understanding what those failure modes are could be quite difficult. Any place you could point someone to better understand all this?
It never hurts to. Furniture has been around a long time, so in general, if you mimic already existing furniture, the proportions, things like that, you're probably going to be in the ballpark. You know, that you should be pretty all right. Honestly, the best thing is just experiment, build
Okay,
something.
I like
Build
it.
it and use it and see what happens, and you learn, right? And that's in engineering, we do that as well. We build a thing and we test it, and maybe it fails early, and we go, whoa, what happened there? And we investigate, and from that you can advance. Now, I've got my bending equations and material properties, and maybe we can link that, some of those documents, in the show notes or something. But um,
Sure.
um, I'd say just the stakes are low in general. I'd say just dive in, start making it, and see what happens.
I'm really glad you said that, because honestly, some of the best how-to woodworking books that I have purchased over the decades are not how-to woodworking books. They're coffee table books with lots of pictures of furniture. The best learning that I've had on how to build furniture is by looking at furniture, going to museums, and every woodworker's done this. Once you start woodworking, you're at a restaurant somewhere and the table starts to rock, not because the legs are uneven, but because and you're looking at the table and suddenly you're crawling around under the table, and your significant other is rolling their eyes at this point. But yeah, observe, pay attention to what's been done. There's very little new under the sun in woodworking, and there are certainly people trying to push the limits, and we've seen some designs that I'm thinking of a Z chair design now. Just imagine a lightning bolt chair, and the joinery at that acute angle where the seat meets the front of the chair. All that stuff is really kind of pushing these, but the answers are in understanding these failure modes and understanding how can we bolster these individual joints, and look at what's been done before. I like it. Good stuff. Wow, we've covered a lot. Wow, we've been talking for almost an hour and 20 minutes. Thank you, Brandon. I really appreciate this. Any place where people can see your work? Do you have an Instagram account or anything you wanna pimp while you're here?
Yeah, I do have an Instagram account. Yeah, I'm still just getting my start, learning every day. But you can find me at Arrow Inspired Woodworks. I'm actually
Arrow inspired.
looking at recently. I'm building my CNC machine right now,
Mm-hmm.
and I'm gonna actually try and start making some Arrow Inspired woodworking. I've got a lounge chair I'm designing that's based on the Wright Flyer. It's funny you mentioned that, but it's got I'm using the same airfoil shape they're using. I'm gonna try and use the same canvas fabric that they used on the Wright Flyer in this lounge chair. Yeah, Aero Inspired Woodworks. You can find me
Very
there on
cool.
it.
Excellent. Yeah, I'd be curious to follow along as the CNC goes up too. But certainly, if you as you make an effort to monetize any of the stuff you're doing, people go follow. Love it. You caught my attention at the Right Flyer right there. That just blew my mind. So awesome. Well, thank you so much for coming on the show. I really appreciate your expertise here, and I hope that people listening to this have learned a little something. I know I certainly did. If nothing else, don't stress about it. Go into the shop and build stuff and then break it. There we go, right? Just
Yeah,
build and break it.
hands on.
Yeah, excellent.